My roll number is 16TE17 and today is about the lecture number 18 of week 11 of DSP. The basic agenda of this lecture is to get familiar with the FIR windowing. There are certain methods about designing filter. One of the methods is about the window method. In the previous lecture, in lecture number 17, we covered the Fourier transform designing. And in the Fourier transform designing, there are certain problems. One of the problem includes Gibbs oscillations. Gibbs oscillations arises due to the sharp transitions, and in this method we will remove the Gibbs oscillations to get smooth transitions. For window method, HWN is equal to H of n multiplied by W of n. Here H of n indicates the Fourier transform method, whereas W of n is about the window method, and through window method we get W of n values, and through Fourier transform method we get H of n values. And at the end we will multiply both of these equations. The common window functions are as follows. Number 1, the rectangular window, triangle window, Hamming window, Hanning window, and the Blackman window. In rectangular window, the WREC n is equal to 1, where n varies from minus m to m. Triangular window, W of tri n is equal to 1 minus n over m. Here n indicates both negative and the positive values. The next is about the Hanning window. Hanning window is mostly used for the smooth transitions and the good roll off, and W Han n is equal to 0.5 plus 0.5 cos n pi over m. Hamming window is usually used for good roll off and the side lobes when maximum. W ham n is equal to 0.54 plus 0.46 cos n pi over m. Blackman window is used for good stop band attenuation. W Blackman is equal to 0.42 plus 0.5 cos n pi m plus 0.08 cos n 2 n pi over m. These all are the windows are applied according to our requirements. Example, consider the 5-tap filter where cutoff frequency is equal to 800, whereas sampling rate is equal to 8000, and there is about a normalized cutoff frequency is equal to 0.2. Here the 2m plus 1 is equal to number of taps, which are equal to 5. As a result we get m is equal to 2. By Fourier transform design we get, this one is the equation, so by applying the Fourier transform design we get h of n values. H of 0 is equal to 0.2, whereas h of n is equal to 0.1871, and using symmetry we get h minus 1 is equal to 0.1871, and the h of 2, by putting the same value in this equation, but here n is equal to 2, we get 0.151. Thus h of n can be written as 0.151, 0.1871, 0.2 is about index, and then 0.1871 and 0.151. As you guys can see that these are the sharp transitions. Now we will find out now we will apply Hanning window. As a result we get smooth transitions, where W of n is equal to 0.5 plus 0.5 cos n pi over m. Here the n varies from 0 to 2, whereas m is equal to 5. As a result we get W of 0 is equal to 1, W of 1 is equal to W of minus 1. As a result we get 0.5. W of 2 is equal to W of minus 2. As a result we get 0. W of n is equal to 0, 0.5, 1 is about index, then 0.5, 0. When we multiply h of n and W of n, this one is about W of n and then this one is about h of n. When we multiply both these equations we get 0, 0.0935, 0.2 is index, 0, 0.935 and then 0. As a result we get the smooth transitions. As you can see that the transitions between 0.2 and 0.0935 are less as compared to transitions which are between the 0.2 to 0.1871. As a result, by applying Hanning window we get our required result, 0, 0.0935 and then 0.2, 0.0935, 0, and we get the smooth transitions. This is our basic requirement. That's why we apply Hanning window, and this is all about the window method, and you guys can apply other methods too.